So before we jump into this, I kind of jumped into examples here. The big idea for this is this idea, and that is that the integral of a rate of change of a quantity whatever that quantity is, man, over an interval so we're talking about a definite integral, gives the change in the quantity on that interval. Now, the way that the fundamental theorem says that basically is that the integral from a to b of f prime of t dt is equal to f of b minus f of a. Since f prime is the rate of change of f, it's the rate of change in the quantity f, then when we would take the integral of that on the interval from a to b, we get the change in f from a to b, which would be f of where it ended minus f of where it started. Okay, and you can apply these to lots and lots of problems. Now, the simplest one, I think, for most people to think about is linear motion. So the position of a particle at time t is equal to 0 seconds is x equals 9 centimeters. The velocity of the particle, v of t, is t squared minus 8 over t plus 1 quantity squared in centimeters per second as the particle moves along the x-axis. So we're just doing what's sometimes called rectilinear motion. It's just moving along a line. For this class, we don't ever get to two-dimensional motion. For BC, we do some of that. That's one of the differences between AB and BC. So for part A, use a graph of the velocity to describe the velocity on the time interval from 0 to 5. So let's grab a calculator and actually look at that. Because I don't know about you, but I have no idea what exactly that looks like. T squared minus 8 over t plus 1 quantity squared. Now you want to make sure that you're only looking at this on the interval from 0 to 5. So we'll go into our window and say, I just want to look from 0 to 5. And for now, at least, I'll leave the x's, the y's as they are. And go, okie dokie. And I'm going to increase the top. The bottom I think is fine, but I'd like to increase the top a little bit so I can see a little more of that. Let's go to 20 and see if that's enough. It may not be. Yeah, it's not quite, but yeah, I'll make it just, I'll go ahead and go up to 30. And then once I get that big a spread, I also, because there's so many tick marks on the y-axis now, I'll change that to 5. You know, being able to adjust your window appropriately is kind of a skill set. Okay. So we wanted to describe the velocity on the interval from 0 to 5. All right. So if we're describing the velocity, we should probably talk about where it starts. So the initial velocity is -8. So the velocity at time 0 is -8, and that would be centimeters per second. They told us what that was. And what do you notice about the velocity? Just anything.
Going up.
Yeah, so the velocity is always increasing. So, and is always increasing. Until t equals 5, when the velocity is, and who knows, maybe that'll be another nice whole number. 223 9ths. That was, isn't that really close to the answer that oh no, it was 120.
Pretty close.
Or something like that.
A huge number over a 9.
Now, you may notice that mine gave it to me as a fraction. That's because I put in the 8 over t plus 1 as a fraction. If you do a slash divided by, I think it gives you a decimal instead. Not positive of that. The other interesting feature of the velocity is it changes from negative to positive, right? So the velocity changes from positive to negative. At, well, we have to find that. It's somewhere between 1 and 2. Find the 0. I'll make the left bound 1 and the right bound 2, and I'll guess 1.23. It's always fun to guess these. Wow, that was pretty good. 1.255. T equals 1.255 seconds. Now, what happens if we were asked to describe the motion instead? So we've got this graph of the velocity. What would we know about the motion of the particle? It's moving along the x-axis.
It's getting faster.
Well, yes, the velocity is increasing the whole time. When I start off, which direction is it moving?
Backward.
Which way is backwards?
Negative left.
To the left. It's on the x-axis, so it's moving to the left. So it would be moving to the left until it got to 1.255 seconds. At that point, it stopped, and then was moving to the right. So actually, in this part, it's actually slowing down. The velocity is increasing, but it's getting less negative, so that's actually slowing down. And then the velocity is increasing the rest of the time. All right, so next it says find the position of the particle at t is equal to 1 second and t is equal to 4 seconds. All right, so the position for t at t is equal to 1 second the position is going to be equal to, well, we have to know that it starts off at 9. That's really important because the integral from 0 to 1 is going to tell me what the change in the position was, because velocity is the rate of change in position. And you don't have to write the whole equation. You can just do this. One of the other nice things about having this in your calculator is that when you go to calculate it, you can come out of this and just go, okay, it's 9 plus, remember, the integral is math 9 from 0 to 1 of, rather than having to type all that again, we already have it in y1. And in your calculator, if you do alpha trace, it pops up all of those y values. So you can go, okay, just y1. Why type all that again with respect to the variable x? It's at 5.3 repeating centimeters. And I said p here, but it's moving along the x-axis. So this is really the x-coordinate, right? And then at t is equal to 4 seconds, I'll go ahead and call it x this time. 9, that's our initial condition, that's where it started, plus the integral from 0 to 4 of v of t dt. And the nice thing about that is I can just do second enter to pull that up again and go, okay, go to 4 this time. And it's 23.93 repeating. All right. Next, we want to calculate both, so two things, the position of the particle at time t is equal to 5 seconds. That should be pretty easy. It's just like what we've been doing. And the total distance traveled by the particle on the interval from 0 to 5. All right, so the position is going to be x is equal to 9 plus the integral from 0 to 5 of v of t dt. And by the way, on the AP exam, if they name a function, when you're writing it as in the integral, you don't have to copy all of that into the integral. You can just call it by whatever name they gave it. I have no idea what that's going to be. I just want this to be to 5. I'm going to guess 31. Yeah, I'm not even close. 44 centimeters. Now, let's find the distance traveled. Notice it says total distance traveled. What this gives me is basically displacement. It's the change in position. That's not the same as the total distance traveled. So you can't just do 44 minus 9 It started at 9, it ended at 44, therefore it traveled 35 centimeters. It's going to be more than that because it was traveling to the left and then to the right. The way that we're going to do that to find the total distance is we want, when it's traveling to the left, to count that distance, and when it's traveling to the right to count that distance. If you're doing it in the calculator, the easiest way to do that would be the integral from 0 to 5 of the absolute value of v of t dt. Now, if you're doing it by hand, what you would have to do is do the integral from 0 to where the velocity changed sign, and that's going to give you a negative because all that was below our horizontal axis. So you'd have to take the opposite of that plus all of the other. But if this is a calculator problem, we can simply do it as the absolute value. So Math 9 from 0 to 5. The easiest place, I think, to find the absolute value is in the catalog. There's other places you can find it, but it's the very first one on the catalog. And then I want to put y1 in there. And it's 42.587. Because it moved to the left first and then it moved to the right. Okay, any questions about that? All right. Let's take a look at some more examples. A car moves along. Oh, I hate this question. There's one like this on the homework. I tell you what, in just a minute, I'm going to find the one that's like this on the homework and tell you not to do it. The problem is that it's all about the units, because it tells you it's got an initial velocity of miles per hour, and then it gives you the acceleration is a rate the acceleration is in miles per hour per second, and it's just a mess with the units. And honestly, on the AP exam, they don't do much stuff where you have to do. In fact, I can't remember any question ever where I saw you had to do something with the units. So let's not do this one. All right, so let's look at something that's not acceleration and velocity and position, which, because you've taken physics, you're used to all that. Here, from 1970 to 1980, the rate of potato consumption in a particular country was C of t is equal to 2.2 plus 1.1 raised to the t power million bushels per year, with t being the number of years since the beginning of 1970. Okay, so one of the things about rate problems like this is they're going to give the rate a name, but this is the rate of change of something. This is the derivative of something. Okay, sometimes students get all tangled up by that. So this is really, B prime. How many bushels were consumed from January 1st, 1972 to December 31st, 1973? Okie dokie. So this is the rate of change in the number of bushels consumed per year. So to find how many bushels were consumed, we're going to take the integral from, we're going to start at 2, and this sometimes bugs students. You're like, well, where are we going to end? Well, this is the end of 2 years later, right? So it's from 2 to 4 of C of t dt. So we're just going to chuff this into the calculator. So math 9 from 2 to 4. Of 2.2 plus 1.1 to the t with respect to t. And because your calculator's dumb, we have to call it x. 7.066 million bushels. This honestly reminds me of, there was a report that came out, I don't remember when, I'm not good at that sort of thing, but it talked about the increase in consumption of vegetables in the United States. And everyone was like, ooh, that's great, we're consuming more vegetables. It turned out that the lion's share of the increase was potatoes in the form of French fries, perhaps not as healthy as people thought. All right. So let's look at some net change from data. The rate at which a pump operates in gallons per minute is recorded at 5-minute intervals in the table below. Approximately how many gallons were pumped during the hour? There are many different ways that we could do this. This is pretty open-ended here. It said, approximately how many were pumped during the hour. If it's on the AP exam, they're going to specify how you should calculate that. Because on this, we could do a left Riemann sum, we could do a right Riemann sum, we could do a midpoint Riemann sum. We could also do a trapezoidal approximation. Generally speaking, unless there's some reason not to, and I'm trying to get something as accurate as possible, I'm probably going to do a trapezoidal approximation. Because then you're using neither the left nor the right, you're averaging those out. You could use a midpoint. Midpoint has certain nicety to it as well, but I'm going to use all the data. So the gallons, and I'm probably not going to be able to fit this onto one line, will be approximately equal to half of 58 plus 60 times 5 plus half, and I'm going to get partway through this and then we're going to switch. You'll see in just a second. Times 5 plus half of 65 plus 64 times 5. And you're like, that's going to be a lot of writing. Can we do it with less writing? And because every interval is 5 minutes here, we absolutely can. We could factor a 5 out of that. We could factor a 1/2 out of it. So 1/2 times 5 times, and then notice, we're only going to use the 58 once, right? But every other one, until we get to the end, we're going to use twice. So that's 2 times 60 because it's going to be part of the first trapezoid and part of the second trapezoid. Plus 2 times 64. Excuse me, 65. Plus 2 times 64. Plus 2 times 58. Plus 2 times 57. Plus 2 times 55. Plus another 2 times 55. Plus 2 times 59. Plus 2 times 60. Plus 2 times 60. Plus 2 times 63. And then when we get to the end, we only use that 63 once, right? Because it's only in the last trapezoid. It's not in the previous one. This is what many textbooks call the trapezoidal rule. And it only works when you have equal width subdivisions. But it's kind of nice. Connor, are you busily putting in all the...
Yeah.
Excellent. I'll do it also, and we'll double check each other. Did you get 3,292.5? Uh-oh.
I probably messed up.
Were we close?
I got 3,582.
Let's see. 58,
Good.
130,
You can do the minimum.
128.
Honestly, I wouldn't be surprised if I made human error.
Oh, I skipped one.
Instead of doing 2 times 63 plus 63, I did 3 times 63.
I did too.
And then 4 times.
And all the 2 times I multiplied them in my head. I think I left off at 116. Hang on a second. Did you get 3,582.5?
I did.
Excellent.
Yay.
Okay, any questions about that?
On the AP test, couldn't you leave it as the
100%.
change?
Yeah, and if you have one like this on the AP exam, you should absolutely not calculate the number unless you need it for a subsequent part. All right, you guys have a great day.